All right, so you being able to identify the difference between a valence electron, an electron in a valence band, and an electron in the conduction band is very, very important, because as we progress, we'll be explaining a lot of events that happens in electronics based on this particular idea. Okay, so it is very, very important that you understand it. Okay, so how is this piece of information useful? Okay, now previously we mentioned that the anode, okay, is positively charged. Okay, now there is a concept in physics about charges, and the concept is this: when we have a positive and a negative charge, they attract. When we have two positive charges or two negative charges, they repel. Okay, it is just like what we have for magnets. Okay, so if I have a magnet and I bring the north pole and I bring two north poles together, they repel each other. Okay, the same thing happens. Two positive charges will repel, two negative charges will repel. If I bring the south pole of the magnet to a north pole, then they attract. The same way, a positive charge would attract a negative charge. So when we talk of a positive charge, I want you to create the mental picture of something that has the ability to attract electrons. Okay, and as we move ahead, you will understand why I'm using the word attracting electrons. Okay, that means remember earlier I said that positive charge, actually if you take a material, the positive charges are the protons, right? But the protons don't actually play a role. Okay, so now what do I mean by positive charges here? If protons don't partake in electronics, but here I'm mentioning positive charges, right? What do I mean by positive charges? Now in electronics, when we talk about positive charges, we are actually talking about the absence of electrons. Okay, we are talking about the absence of electron. Now how is this so? If you take any atom, let's say copper, I think copper is the 29th element, right? The atom would have equal number of protons, which are positively charged, and equal number of electrons, which are negatively charged, right? Now, so far as the number of positive charges equals the number of negative charges, we have a neutral atom, because the total positive effect is cancelled by the total negative effect of the electrons, right? But then, if I should take away some electrons from the atom, let's say I take a single electron, then now, you see, by taking a single electron from the atom, it doesn't change the number of protons in the nucleus. So the number of protons still remain 29, but the number of electrons now become 28. If I take another electron, electrons now reduce to 27, protons still maintain 28. That means that there will be now two positive, a positive effect from two positive charges, right? So that means that it renders the atom positively charged. Is that okay? The same way, if I should add an extra electron to the copper, so that it becomes 30 electrons, by adding that electron, I don't change the protons, right? So that means that I'm going to have an extra electron that doesn't have any proton cancelling it. So that means that atom becomes negatively charged. Okay, so basically when we refer to positive charges in electronics, we are talking about the absence of electrons. Okay, and when we talk about negative charges, we are talking about excess electrons. So I need you to get these things right. Okay, positive charges means excess electrons, negative charges means positive charges means the absence of electrons, and negative charges means we have excess electrons. Okay, these things will come in very handy. Now, if we are saying that the positive charges are merely absence of electrons, then why are we treating them as particles, right? Well, it happens that when we can actually treat them as particles, and I like to call them fictitious particles, particles that are created out of fiction. We all know scientific fiction, okay? Things that are created out of the imagination of people. Okay, so they are not necessarily particles like we have electrons, okay? They are just a notion. The fact that an electron was supposed to be somewhere and it is not there, okay? But we are still able to think of it as particles, and it makes our models work appropriately, okay? Now, the negative terminal we call cathode, and so if the positive terminal is capable of pulling or attracting electrons, then what do you think the negative will be doing? Of course, it will be releasing the electrons. So the electrons are released from the negative and it goes to the positive. Now, take note of this. Electrons are released from negative and it moves to positive. If we reverse the situation, we can also say that the positive charges move from the positive terminal to the negative terminal. Because if an electron is leaving, it is leaving behind a space. Is that okay? Take it as if you are in a car and you look outside, it rather feels like the ground is moving. Is that okay? So we call it apparent motion. Is that okay? So though naturally or technically what is happening is that electrons are moving from the negative charge terminal to the positive, we can equally say that positive charges, the fictitious positive charges, are moving from the positive terminal to the negative terminal. Okay, so don't be confused about these things. Okay, so for the valence electron to participate in electronics activities, we first need to get it into the conduction band. Okay, so even though I mentioned that it is for electronics, it is the valence electrons that do the work, the valence electrons have to first move into the conduction band. Is that okay? That is a requirement. Valence shell first have to get into the conduction band before it can contribute to the activities or business of electronics. Now, I've been mentioning band. What are these things and how are they useful to us? Is that okay? Before we can move an electron from the valence band, we have to put in energy. Okay, this energy could be thermal energy, it could be light energy. Okay, so the fact that a solar panel is able to generate electricity is because the materials, okay, the solar cells absorbs energy from the light that is incidenting on them, and that energy that is absorbed is used to excite an electron from the valence band into the conduction band. Is that okay? Now, if you take different materials, you realize that there is they have different materials have different amount of energy that is required to move an electron from the valence band into the conduction band, right? Take it as I want an analogy, nothing is coming to mind, right? But basically I think you should get it, right? So there are certain kind of materials, it is almost like you just need very little energy to do that, okay? Just a little energy, and you have your electron excited from the valence band to the conduction band. Is that okay? So pictorially, we can read like, assuming this yellow band is the valence band and this blue one is the conduction band, it's almost like the conduction band sits on top or it overlaps with the valence band, okay? Because the little amount of energy you apply, you have electrons exciting into the valence band. Now, these kind of materials, examples include silver, copper, and gold, okay? Very little amount of energy is required to excite their valence electrons, and there is a name for them. The name of this material, we call them conductors, okay? So a conductor basically is any material that requires very little energy or practically no energy, but let's just stay with very little energy to move electrons from its valence band into the conduction band. Okay, so it's like their conduction band sits right on top of their valence band. Okay, little energy and you are gone. Okay, so conductors, an example, like I said, you have silver, copper, and gold. Okay, all right. Now, we also have another group of materials. For them, the amount of energy that you require to excite even a single electron is so huge that sometimes if you don't take care, you end up deforming the material before you even excite the electron. Okay, these materials do have a name. Okay, so pictorially, if you look at this one, the valence band sits here and we have a very huge gap. So the gap here represents the amount of energy that needs to be supplied, right? Have a very huge gap here before you get to the conduction band. Now, these materials that have this property, we call them insulators. An example is diamond, glass, and paper. Okay. By the way, what is the best insulator on earth? Let me first ask, what is the best conductor and what is the best insulator? Write this down. I'll take the answers in the evening session. Okay. Very, very interesting. Okay, so we now know that some materials is so easy, little energy, and we excite electrons from valence into conduction band. Other materials, we need a huge amount so that we may even end up deforming the material. Okay, so it's practically to say that it's impossible to excite an electron in them. Let's just put it that way let's just put it that way for now. Okay, now there is a third category of materials. They require more than what conductors require, but they don't require that much as required by insulators. Okay, so their electrical properties actually sit between conductors and insulators. Okay, well, so these materials are called semiconductors. So the name defines it. Conductor. Okay, so somewhat a conductor. Okay, right. Now these guys, I put it as they require a moderate amount of energy to excite an electron from the valence band into the conduction band. Now let me just remind you that the reason we need the electron to be in the conduction band is because until the electron gets into the conduction band, it cannot contribute to current. Is that okay? An electron has to be in the conduction band to contribute to current. Okay, so they are not really as high as insulators and not as low as what? Conductors. And I've been talking about energy, excite them. Where does this energy come from? This energy can come from the environment, okay, temperature, okay. The little heat you give them, the electrons can absorb energy. The energy can also come from light, as in solar panels. The energy can also come from what we call an applied electric field. Okay, if I connect electricity to the material, yes, I can give it energy to excite the electrons from the valence into the conduction band. Now, how does this help us? Or what is the use of all these things, energy band and conductors, and why do we need this? Okay, great. So when you take conductors like copper, right? We are always talking about copper is a good conductor. Why? The fact is that the amount of energy, as we already said, that is required to move the electron from valence to conduction band is so small such that even at room temperature, and when we talk of room temperature, we are talking about normal room conditions, but there is a value for it, which is what do you call 25 degrees Celsius. Is that okay? I don't know why they call it room temperature. Definitely not in Africa, because my room temperature is never 25. Okay, so that was just by the way. So even at room temperature, okay, when we haven't actually added any energy to the system, there are already electrons around that can contribute to current. Okay, so that's why copper has that excellent what do you call it, excellent conductivity. Okay, we don't need to put in energy to excite the electrons. So far as the copper is within room temperature, it already have enough electrons moving about that can do the work of generating what, electric energy. Is that okay? So that is one reason. Now, as a result of this, you see, this same thing that makes copper an awesome conductor also has an issue. Okay, it means that as engineers we don't have much control over copper's conductivity. Okay, because even at room temperature its conductivity is excellent. So I mean, just imagine you trying to reduce copper's conductivity or control copper's conductivity. That's almost impossible. Is that okay? A lot of energy has to be put into that, which is not something we would like to do. Okay, we basically want to spend less energy when we are dealing with electronics. So we don't like systems that would require us to put in too much energy. Okay, so yeah, their ability to have good conductivity even at room temperature is a good thing, but it's also their flaw. Okay, it's also their problem, because now it makes it challenging to manipulate their conductivity. Okay, but then if you look at semiconductors actually presents engineers the opportunity to manipulate their conductivity. Okay, because they don't require that much as for insulators or that low as for conductors. It means they allow us room to engineer how good conductor they should be or how good insulator they should be. Is that okay? And it happens that this is what actually led to the revolution in electronics. That the fact that we can adjust the conductivity of semiconductors. Okay, now if you want examples of semiconductors, you have silicon and germanium. I know silicon is more popular, probably everybody has heard about it. Okay, so when for electronics to change, you know, those days they were using a lot of big stuff, triodes and all that, until they discovered semiconductors and realized that we can actually interfere with the conductivity of these materials, right? Then there was a revolution. Okay, they started creating transistors, started creating integrated circuits and all that, right? Just because of the fact that we are able to engineer how good the conductivity of a semiconductor should be or how bad it should be. Okay, and it happens that, you see, whether good conductivity or bad conductivity, everything has a function, everything has a use, right? For instance, we don't use conductors to insulate other conductors. If you want to insulate other conductors, you need insulators, right? The same way, conductors also have good thermal properties. So all our kitchen saucepans and stuff, they have insulator handles. Okay, so everything has its space. Okay, so nothing is that bad. So the fact that we can decide whether a semiconductor should become an insulator or become a conductor actually gives us much control than it's naturally being a conductor or naturally being what, an insulator. Okay, all right, so I already explained this. Now, when you are choosing materials, okay, and this, in fact, this extends beyond electronics alone. Okay, when you are choosing materials for an electronics task or something, okay, you are not supposed to just look at the electrical properties. Okay, there are other things that you have to pay attention to. Now, if you look at this chart of conductivity, you realize that silver has the best electrical conductivity. But then, mostly we are talking about copper. Every circuit we are talking about copper. In fact, silver is scarcely used. Or yes, So before you can see silver being used in an application, then we really require a very superior conductivity, right? And mostly we are dealing with copper. Okay, so why is it so? Okay, so it happens that you don't just look at the conductivity to choose the material. Some other factors that you should consider would be cost. Okay, silver is really expensive. Okay, I mean, you don't want to build a torchlight that will cost like 100 US dollars. Okay, if you are building a torchlight, you want it to cost like 10 US dollars at most, so that a lot of people can buy it. Okay, but if in the end you have to spend like 50 US dollars just to acquire silver for the conductors, then you realize that it is an unnecessary cost. Is that okay? So cost is a factor, one crucial thing that you should always look at when you are building systems. You should also look for availability. Okay, copper is actually abundant in on earth. Silver is quite scarce. Okay, that's also the fact what contributes to its high price. Okay, then we also have durability. We also have other physical properties. Okay, in terms of reactivity, silver reacts very fast with the atmospheric conditions than copper. Is that okay? Now, why do we prefer copper over silver? You see, if you look at this table here, uh, look at the order of magnitude. They are all 10 to the power 7, 10 to the power 7. And the difference between this and that is just about 1 point something, right? So technically, silver is not any much higher in terms of conductivity than copper, right? So looking at all the cost that you would have to incur just for that little gap of conductivity, you just fall on copper, and copper is actually excellent, right? So that's why in the industry we are always talking about copper. Of course, there are instances where we talk about aluminium, and though aluminium is the fourth best, sometimes we choose aluminium over copper because aluminium also happens to have some properties that makes it ideal in certain situations. For instance, high tension cables, right? You don't use copper, even though copper has a superior conductivity than aluminium. They use aluminium because aluminium is lightweight compared to copper. Okay, aluminium is called lightweight. So for the same, I want to coin a term. Can I say conductivity per unit density? I'm just hoping that is something. Okay, conductivity per unit density. Then aluminum will have a higher conductivity than copper, right? Because copper is very heavy. Okay, aluminum is lighter, and we don't want those heavy stuff hanging over our neck, right? And it also happens that aluminum is actually corrosion resistant. Yeah, aluminum doesn't corrode. Copper corrodes, iron rust. You can find out the difference between corrosion and rusting. FYI, rusting is a more intensive form of corrosion. It happens that aluminum doesn't corrode, right? So you can just hang it there and don't worry about whether it will corrode or not. But copper does corrode. Okay, it creates oxides when it reacts with atmospheric moisture and oxygen. Okay, so yeah, that is that. We don't just choose things. You should understand and have a basic foundation or a reason for the choices that you are making. Okay, please, I need you guys to really pay attention to this. Okay, so yeah, I think I've already talked about this cost, fabrication, and other stuff. Okay, now electrostatics. Okay, so I think I'll pause here